The McGill Robotics Mars Rover team drew valuable experience from last year's performance at competition in designing a cutting-edge rover for this year's URC. Today, we're proud to introduce Boomy.
The mechanical division has been working hard on a brand new design with tons of new features. First, we have the drive system. Thanks to our custom design, the motor is now hitting completely inside the wheels and protected from obstacle impact by an aluminum housing. Next, the suspension. The double lambda rocker body worked well for us last year, so we've made it lighter, stronger, and even more modular. We can now switch between 6-wheel and 4-wheel drive in a matter of seconds. The frame is made of welded steel tubing, incredibly light and rigid. Improving on last year's design, the differential system has been changed to a bar design, now with virtually zero backlash. Finally, we have the arm. This state-of-the-art manipulator has 6 degrees of freedom. It has a 5-kilogram payload made possible with harmonic speed reduction.
This year, the electrical divisions focused on designing a feature-rich system without compromising on modularity or reliability. Each of Boomy's 4 LiPo batteries have their voltage, current, and temperature continuously monitored. Our hot swap circuitry allows Boomy's batteries to be changed on the fly, while our load-sharing circuitry ensures that they're all drained evenly. Boomy's drive system is composed of flat brushless motors controlled by dedicated drivers that provide a finer degree of control than off-the-shelf solutions. The arm's brushed motors are driven by off-the-shelf controllers running at ultrasonic frequencies to improve efficiency and reduce electromagnetic interference. Contactless magnetic encoders provide absolute position measurements of the arm's joints with 13 bits of precision.
This year, the software division tried to innovate and implement advanced features that would be a stepping stone towards a future fully autonomous rover. We focused mainly on environment perception, and using a tilting LiDAR, we can now map the terrain in front of us. This allows us to better understand the geometry of the field, much better than with cameras. In the same branch, we are now using visual odometry with optical flow as an additional source of position estimation. Combined with the standard wheel odometry and GPS data, we can get a very accurate position estimation. Additionally, we pointed a high-definition camera towards a conical mirror. This gives us a 360-degree panorama, which we can unfold to get a standard video feed. Finally, with all the modifications made to the arm, we had to redesign its control system. We derived the forwards and inverse kinematics to establish a global control system. This gives us the ability to control every joint on the arm based on the target position of the end effector.
This year's Rover Science is a significant improvement on the previous iteration. We have an auger collecting a soil sample from within the ground and a surface rock being collected by the arm. Temperature sensor measures temperature directly within the ground, and a conductance-based humidity probe, once the sample has been transferred to a sealed cache, measures the soil water content. Finally, the rover conducts Raman spectroscopy. Our spectrometer has a modular design with a 3D printed case. The optics are based on a Czerny-Turner design, and we use a 785 nanometer laser. Back at the command station, the samples undergo additional testing. We measure soil pH, perform qualitative stains for biological molecules, and do gram stain microscopy. The data that we obtain on the rover and on the bench is then compiled and allows us to draw broad conclusions about the geology and the biology of the site that we investigate.
We're pleased to announce that we managed to keep our rover on budget and that we're currently planning our trip to competition. We're on schedule, we're actively testing, and we are looking forward to meet everyone at NDRS.